Hello everyone, my name is Bailey Jarrett and this is my Project 2 for Math 4753. This project will focus on simple linear regression and using this with real data. The data I have chosen to use comes from the smeltpot.csv file. This dataset contains 3 distinct variables. One of the variables is brick, which is qualitative and gives just an A, B, C, D, and E name for every type of brick. There's one of each. There's also a porosity and diameter variable, which are both quantitative and continuous. Different types of bricks are used to line aluminum smelter pots. The American Ceramic Society collected data to conduct research on the properties of bricks used to line these smelter pots. They measured the apparent porosity and the mean pore diameter of different types of bricks that are used to line the inside of these smelter pots. They hypothesized that if they can know more about the properties of these bricks, they can determine the life length of the smelter pots. They say that the higher porosity of these bricks leads to a shorter life length of the brick and the aluminum pot itself, and vice versa. While this is all well and good, what I am here to determine is whether or not there is a linear relationship between porosity and the diameter, which I will be using simple linear regression to determine. But before I can get there, I need to first dive into the theory behind simple linear regression. Simple linear regression uses an independent variable and parameters in a linear combination to build a regression that estimates the mean. That estimation is called a trend. The more accurate the model is, the more accurate the estimations of the dependent variable are. So, we are given that yi is equal to beta naught plus beta 1 xi plus epsilon 1. Now, these variables seem confusing, but all they really are is beta naught is the y-intercept, beta 1 is the slope, and epsilon 1 is the errors within the variable. It can be said that the errors are distributed normally with a mean of 0 and a variance of sigma squared. So let's first take a look at the expected value of yi. We've done this many times in class. All we need to do is plug in the equation for yi. Through our rules, we know that the expected value of a sum is equal to the sum of the expected values, so we can separate them, take out the constants, the expected value of the error leaves the planet, and we're left with the expected value of y given xi is equal to beta naught plus beta 1 xi. This expected value of y given xi is called the trend, or the estimation of the mean that we talked about previously. Additionally, we can also say that yi is distributed normally with a mean of beta naught plus beta 1 xi and a variance of sigma squared. Now let's take a look at the expected value of the error, and let's prove that it's 0. Epsilon I hat is known as the estimation of the error, which is also known as the residual, or Ri. If we go down here, we take the sum of the residual, which is equal to yi minus the estimation of yi. We can then plug in the equations for yi and y, and we end up getting that the summation of the residual over n, the number, is equal to 0 over n, which is equal to 0, therefore proving that the expected value of the error is 0. Furthermore, in relation to beta I, more often than not, beta I values are equal to the estimation of beta I, or the beta I hat. When this is the case, it means that beta I hat is an unbiased estimator of beta I. We can have this estimation be over the entire expected value, so therefore the estimation of the expected value of y given xi is equal to the estimation of y, which is equal to beta naught hat plus beta 1 hat xi. Notice that the epsilon is not there because it equals 0. Now we're going to go ahead and prove that the expected value, or that beta naught, beta 1 hat and beta naught hat are indeed unbiased estimators of beta 1 and beta naught. First off, with beta 1 hat, we plug in the equations. So expected value of beta 1 hat is equal to the expected value of the sum of ai, yi. From there, we use our rules and split things up. And we end up getting the expected value of beta 1 hat is indeed equal to beta 1, making an unbiased estimator. Again, through a similar process, we can do the same thing with the expected value of beta naught hat, and we end up finding the same thing, that the expected value of beta naught hat is equal to beta naught, making beta naught hat an unbiased estimator of beta naught. Now, with all that theory out of the way, let's dive into our data. First, we did a very basic trend scatter of our data, and from what we can see, there could be an argument to make a linear model that would fit the data. However, when looking at the data, you could also make the argument that a quadratic would also fit, and so that's exactly what we did. We went through and used the Shapiro-Wilk test to test for normality, both for the linear model and quadratic. The p-values were the exact same, 0.868, which is much greater than the alpha of 0.05, which means we cannot reject the null hypothesis that the residuals is distributed normally. Therefore, the null is plausible. This test, while helpful in determining normality, did not help us determine which model was better than the other, so we need more testing. We then test constant variance, both linear and quadratic. I'll be flipping back and forth between the next two slides. As we can see here, the first graph of the linear and the quadratic fit shows the residuals versus the fitted values. Ideally, we want the solid red line to be as straight as possible and to be as close to the solid black line as possible. A straight red line indicates that the mean residuals for each section are more or less equal. The solid black line represents r equals 0. The closer the line is to this r equals 0 or regression line, the better our model fits the data. As we can see between these two, the quadratic is obviously the straighter and better fit. It is both straighter, smoother, and closer to the regression line over a greater portion of time. The second graph on each of these pages does the exact same thing as the first. It plots the residuals and the fitted values, but it uses the trend scatter. It plots the trend scatter as we used earlier. Again, we would also want the red line to be as straight as possible, and we would like it to be as close to the regression line as possible. Again, based on these two graphs, it would lead me to believe that the quadratic model would be the best fit, but let's continue to investigate to be sure. If we look at the adjusted r-squared values for each, the adjusted r-squared is very similar to addition r-squared, except it takes into account the complexity of the models we're trying to build. The adjusted r-squared for the linear model is only 0.55, while the adjusted r-squared value for the quadratic model is 0.8. With this being much higher, this means that the quadratic model better explains the variability in the data, which leads me to believe that the quadratic is the one that we should use. So, that's exactly what I did. I went in and fit a curve with our data, and as you can see, the quadratic fits rather nicely. There is a portion where the quadratic curve dips outside of the plot. However, this could be attributed to the lack of data points that we have in the estimation. If we look at the summary of our quadratic model, at the top it gives us our formula that we've been using. Then it gives us our residuals, which give us a good indicator of our range and our quartiles. Then we can really dig into the coefficients, our intercept or our beta naught hat. We have our porosity, which is going to be our slope, which is beta 1 hat. And then we have our x squared term, which is the curve of the quadratic, or our beta 2 hat. The standard error helps us calculate the t-values, and the t-values are actually just going to be the coefficients divided by the standard error. So that first one, 2.834, is actually just going to be the 18.6, divided by the 6.5. Lastly, we move down to the residual standard error, which gives us a good idea of the error and the residuals allows us to comment and speak towards that. The lower or closer to 0 this value is, the better. Ours is only 1.4, which is just fine. The last thing I want to talk about is the f-statistic and the p-value. These really tell us whether or not our model is doing what it's supposed to, if it's working for the data set that we have. For the f-statistic, we really want that to lie within our acceptance region, which ours does, and our p-value needs to be relatively small, which, again, ours is. We then went forward and made confidence intervals. The above code there was created confidence intervals for all variables within the model based on the default alpha equal to 0.505. The way to check if these intervals are good is seeing if our variables lie somewhere in the middle, which it appears they do. We then wanted to make logical predictions based on our linear model, or quadratic model. The predict function takes the independent data from our set and uses the model, our quadratic model, to make logical predictions about what the dependent variable might be. Lastly, we looked at Cook's plot and Cook's distance. Cook's distance gives us a visual representation as to how much of an effect each data point has on the whole set. Judging from the one we have here, our fourth data point really affects our model and our data set the most. And so I went through and took that data point out of our quadratic model. I thought this might have some significant effect on it. However, it appears that it did not change anything significantly. We still have a very similar, the exact same even beta naught hat, beta 1 hat, beta 2 hat, f-statistic, p-value, adjusted r-squared, the whole 9. So to conclude, we set out to see if there was a linear relationship between the porosity and the diameter of different bricks used to line smelters. Based on our data and our models, we cannot say that a linear relationship is impossible, but we can say that the quadratic relationship better fits the data set than a linear one does. The linear model was not a bad approximation. In fact, it had an adjusted r-squared value of 0.5 and a p-value of 0.05, but we quickly realized that a quadratic model was better at estimating our data, and with an adjusted r-squared value of 0.8 and a p-value of 0.02. The only issue I had in dealing with this data set was the very small number of data points that we had to work with. It makes it really hard to generalize these models to a greater population or even just a sample. There is also only one data point per type of brick. With multiple data points from all 6 types of bricks, we can redo these tests not only to get models that would better fit the data set as a whole, but also get models for each brick type. Upon this further testing, perhaps we find the data as a whole to be modeled best as a quadratic, but some specific types of brick could best be modeled by linear fits. Thank you.